So good morning to all. This is our first lecture of the course Fluid Mechanics. Okay, and the course code for the same is ME210. Fine. So let's first discuss about the instructor and TA. So perhaps those who are in third year, to them I have already taught a course on IC course on engineering thermodynamics, particularly for your batch. This is no more institute course. This is now a departmental core course, and all the second year students I think are taking this course parallelly in this semester, and maybe Dr. Atul is teaching to you. So, I am Pramod Kumar from School of Mechanical and Material Engineering, okay, and I will be teaching you this course on fluid mechanics. And along with this, there will be two teaching assistants. One is Rahul Kumar Mandal and another is Sandeep Kumar. Both of them are the PhD students in School of Mechanical and Materials Engineering. And today Sandeep is there, so he will be taking your attendance. So let's now see the syllabus for this particular course. So in this course, if you see the LTP scheme, so we have 2.5 lectures, 0.5 tutorials and no practical. So the meaning of 2.5.5 is that after every 5 lectures, there will be one tutorial. Is this point clear? So after every 5 lectures, we will be having one tutorial session. Okay. Now, if you see the syllabus for this course, so syllabus is actually split into 7 different modules. So first module is about the definition of the fluids, then what are the different hypotheses that we use for solving or analyzing the fluid flow problems, and then particularly we will also study the different types of flows and different types of fluids. Okay. Then we have fluid statics, where Pascal's law is one of the important law which you have studied earlier also, but we will try to see all these concepts now in more deeper sense. Okay, and then there are the different concepts. For example, the forces acting on the fully or partially submerged body, and then buoyancy and stability of the bodies, etc., which are just on the surface of the water. Okay. Then we have fluid kinematics, where we will try to see the Lagrangian and Eulerian description of the fluid motion, and within this then we have some other concepts which are particularly related to the acceleration of the fluid, okay, in a flow fluid. Then we have fluid dynamics. So here we will try to see some governing laws, and then how these governing laws are applicable for different types of fluids and different types of flow situations. Okay, and then we have internal flows. So the meaning of internal flows is, if you are having a solid object and say flow of fluid is happening through that. So one of the common example is when you pump water at your house. So how do you pump water? Or say, how does water come to tap from a tank? So you are having some pipes. Okay, so these pipes are nothing but some solid structures through which flow of the fluid is taking place. So if you see the flow which we receive at the tap, the water which we receive at the tap, that comes through internal portion of that particular pipe. Okay, so that is something which we will try to see over here in this module of internal flows. Then we have dimensional analysis. So if you see a fluid dynamics problem, there will be plenty of the variables involved. Okay, so analyzing the fluid dynamics problem with large number of variable sets becomes challenging. So what we do typically, we try to reduce the number of variables. How we can reduce the number of variables? We can reduce the number of variables by doing this dimensional analysis. Okay, so maybe if you people might have heard of the term Reynolds number. Okay, so I think all of you know the definition of the Reynolds number. So if you see, velocity of the fluid flow and diameter of the pipe are separately two independent parameters. Similarly, if you see, density of the fluid and viscosity of the fluid are also the two independent parameters. But whenever we consider Reynolds number, so effect of all these parameters are actually coming into a single non-dimensional number. So that is something which we will try to see, the dimensional analysis, that how we can actually non-dimensionalize different parameters to get the set of variables which are non-dimensional parameters and having combination of multiple variables, so that for a simple flow field actually we can reduce the total number of variables. Okay. Then we have finally the external flow. So external flow is very common. You see automobiles, aeroplanes, trains. So number of objects are actually moving in the atmosphere. So when these are moving in the atmosphere, in the surrounding we are having air as the fluid. Okay. So what happens actually, the interaction of all these objects happens with the air. So that is typically referred to as the external flow. Okay. Is this one clear? So these are the 7 different modules which we will be studying in this course, and if time permits then we will try to see certain application aspects of the fluid mechanics. So for example, one of the important application of fluid mechanics we see nowadays in electricity generation. Okay, so if you see, typically we are located in Himachal, so it's a hilly state, and Himachal is having a number of hydropower plants. Okay, so hydropower plant is nothing but what they are doing. They are employing the energy of water to first convert it into electrical energy, and once it is converted into electrical energy, then what they are doing? Into mechanical energy, and once they convert it into mechanical energy, then further they are converting into electrical energy, and whatever like fans, lights you are seeing over here, this is nothing but say coming typically in Himachal, we can say that it is coming from a hydropower plant. Okay, so though there are a lot of, earlier there used to be a time when majority of the energy used to come from coal based thermal power plants. Okay, but now there are environmental challenges as well as the depletion issue of the fossil fuels. Okay, so say resources of fossil fuels are actually depleting. So that is, these are one of the important concerns where actually what we are doing now, we are shifting towards the alternate sources of the energy, and hydropower is also one of the promising source of energy. And for using hydropower, what we have to do is basically we have to apply the principles of fluid mechanics. Okay, so if you have to say understand how a hydropower plant works, how the power of fluid is getting converted into mechanical energy, what are the mechanisms, what is the amount, how to estimate the efficiency of the hydropower plant. So all these concepts you can apply if you have the knowledge of fluid mechanics. Okay. Then let's talk about very important things. So we have to see that what are the textbooks which you can refer. So first 2 are the important ones I have given with the different color. So FM White of fluid mechanics, this is primarily the textbook prescribed in your syllabus for this course. Then along with this book by Sengel and Simbala, Fluid Mechanics Fundamentals and Applications, this book also I will be following almost to the similar extent. So whatever I will be discussing in the lecture, that will be mainly from these 2 books. Okay, is this point clear? Then there are many other books. So for example, this Pritchard, Michel Fox McDonald. So this also for certain topics I can refer, or those who want to get into the deeper knowledge of the fluid mechanics, they can go through this book. Whenever you are in class, please don't use mobile phone. If I see anyone using the mobile phone, then I will be taking it. Okay, then Kundu and Cohen. This is also a good book of fluid mechanics, so you can refer to it. Then beyond this, this is a book by Rust French. So this is book on fluid mechanics, an introduction to theory of fluid flows. So particularly those who are interested in deeper insights of the fluid mechanics, they can actually more deeper insights, say from molecular perspective, at molecular level what happens, how the different molecular equations gives the viscosity, thermal conductivity. If you are interested in knowing all these aspects, that you can refer to this particular. Okay, so all are clear with the books. Then next comes prerequisite for doing this course. So typically engineering thermodynamics is considered as the prerequisite for fluid mechanics, because in this course we will be referring to a number of properties. Okay, and these properties, if we have to define for a fluid, so the fundamental basis comes from nothing but from the thermodynamics. Then after that, what we will be doing, we will be analyzing the different fluid flow and fluid flow systems. Okay, so for analyzing the fluid flow systems, if you see in thermodynamics, there are two approaches. One is called as system approach and second one is called as control volume approach. Okay, so these concepts also initially typically are discussed in engineering thermodynamics, and after that we refer to this course, but as it moved now from institute core to departmental core, so that's why this course you are doing parallelly. So what I suggest is whenever you are studying the concepts of thermodynamics, there also you try to relate the things properly, because some of the initial things, for example defining properties, how to define control volume, all these concepts will be coming from there as well. But whenever I will be discussing over here, a brief idea I will try to give over here as well. Okay, is this point clear? Then we have attendance policy, which is very important thing. Okay, so in order to appear for mid semester and end semester exams, you must have minimum attendance of 80%. Okay, so 80% is the institute's attendance criteria, so I will be following strictly that one. Fine. Then next is the evaluation scheme. Okay, please carefully note it down, because evaluation scheme is also important aspect. Don't come later on that this component was having these many marks, or I forgot to submit the assignment because I thought it is not part of the evaluation scheme. So that's why it is very important to know evaluation scheme at this moment. Okay, so if you see, evaluation scheme comprises of 4 different components. So the very first is assignments. So typically, as there are 7 modules, so I will be giving you about 5 to 6 assignments. You people have to submit all the assignments, 5 to 6, okay, out of which only 2 will be evaluated. Now which 2 will be evaluated, that will not be announced in advance. Okay, so that I will be choosing which 2 I have to evaluate. So don't come later on by saying that, sir, I didn't submit only assignment number 5 and you have only evaluated that. Because I am announcing on the very first day itself that you will be given 5 to 6 assignments, out of which you have to submit all. But I will be randomly deciding any 2, okay, which will never be announced. Even if you are getting marks of assignments, then also it will not be announced that which 2 were evaluated. Okay, so randomly I will be evaluating any 2, and each assignment will be of 5 marks. Fine. So all are clear with this. So make a note of this very clearly, because later on people come and then say, sir, can I submit now? This is the only assignment I have not submitted. So When marks are shown for assignments, after that you cannot submit the assignment. Fine. Then we have mid-semester exam. So mid-semester exam for the course will be having weightage of 30%. So 30 marks will be for mid-semester exam. Final exam will be having 50% weightage. Okay. And then I'll try to see if a mini project kind of thing can be given where you can like explore certain applications of fluid mechanics. Okay, because you have known the concepts. Now using these concepts you can, with the help of a mini project, you can try exploring, or say it can be on reading aspects, that you have to say read some recent work related to fluid mechanics and then prepare a summary of that also. It may be like that. Okay, so that will be of 10 marks. So exact what will be the exact topic for this, that probably I will be announcing after the mid semester, because by mid semester most say you will be having good idea of the concepts, fundamental understanding of fluid mechanics. So then we will try to see these things. Okay, clear? So all of you have noted the evaluation scheme. Now you should not tell me that this was not informed initially. Okay, because I have spent almost 3 to 5 minutes on this one. Okay, now let's see the idea of the subject. So very first thing, whenever we study a subject, first we try to know its introduction, or say definition. What is fluid mechanics? Okay, so before knowing the fluid mechanics, you must know first what is mechanics. So can any one of you answer? Okay, one more thing. Have you people referred to gone through a course of continuum mechanics? No. Okay, no problem. So what do you mean by mechanics? Any one of you, if you want to answer it? You need not to answer it perfectly. You can just give a vague idea as well. Okay, study of motion. So we are having different objects. Now these objects can be at rest. These can be in motion whenever these are subjected to under the effect of some external forces. Okay. So when typically, so the study of objects either at rest or in motion under the effect of some forces, that we call as nothing but the mechanics. Now when the object is at rest, okay, if object is at rest, then whatever the application of mechanics or branch of mechanics we apply to objects in rest, that is called as statics. And when the object is in motion under the effect of forces, then whatever branch of mechanics we call, that we call as dynamics. Okay, similar to this, if I simply make a statement that my object is not generic, okay, my object is not generic, like I am not saying that it's a solid, but what I am saying it's a solid or fluid, I am specifically saying if my object is fluid and I am analyzing a fluid element either at rest or in motion under the effect of forces, then particularly I will be calling the study of this type as nothing but fluid mechanics. Is this point clear? Now in fluid mechanics also, whenever we are talking about fluid at rest, then we call fluid statics. Okay, when my fluid is at rest. Is this point clear? When the fluid is in motion, then we call so this is when fluid is in motion. Fine. Now typically when we talk about fluid mechanics, okay, so fluid mechanics can also be classified in large number of other ways. Particularly in fluid mechanics, when we only talk about liquids. So till now I am referring to a term fluid. Now fluid can be a liquid or it can be in a gaseous phase. Liquid and gas both together can be put into a category of fluid. But if I only refer to the situation that I am applying the concepts of mechanics only to the liquids, if I apply concepts of mechanics only to the liquids, then we call it specifically as nothing but hydrodynamics. Okay, so when I am applying fluid dynamics only to the liquids, then I will be calling it as hydrodynamics. When I am considering that it is only liquid, but liquid is also at rest, then I will be calling it as hydrostatics. Is this one clear? So what I am trying to say is, apart from the very generic categorization which is fluid statics and fluid dynamics, there are other number of categorizations of fluid mechanics which are based on different criteria. So one of the criteria which I have mentioned over here is that if you are only dealing with a special type of fluid and that is a liquid, then I will be calling it as nothing but hydrodynamics. If I am dealing with liquid at rest, then I will be calling it as hydrostatics. If I am dealing with a gas, then I will be calling it as a gas dynamics. When I am only dealing with a liquid, with a fluid which is in gaseous phase, then we call it as gas dynamics. So what are the applications of gas dynamics? If you see typically your aeroplane engine. So what happens in case of aeroplane engine? You are having multiple gases which are passing through that gas turbine engine, and the speed of these gases is very high. Okay, so there what happens basically, the density of the fluid does not remain constant. Density of the fluid keep on changing. Similarly, if you have a aeroplane moving at very high velocity and that aeroplane is interacting with the surrounding air. Obviously in the atmosphere what you have is air. So whenever aeroplane will be interacting with the surrounding air, and if it is moving at high velocity, then also we will be finding that in different locations of the flow field we will be having different values of density. Okay, so under this scenario what we will be having changes in density of the medium. Okay, so whenever we are involving the gaseous medium with variable density, then we typically call our subject as nothing but the gas dynamics. Is this one clear? Then we have few more very specific terminologies. So for example, one we call is meteorology. So what is this? If you do study the atmosphere and atmospheric phenomenon. So atmosphere is also consists of fluids only. Okay, and all the atmospheric phenomenon which are taking place, these are also nothing but the, what are the atmospheric phenomenon involving? Majority of the atmospheric phenomenon. For example, from sea or ocean, what is happening? Evaporation of the water is taking place. Then you are having precipitation in the form of water droplets, cloud formation. So all these nothing but are the phenomenon which are involving fluid, but these are involving at a very large scale. Okay, so which is involving your atmosphere. Okay, so this type of branch of fluid mechanics that deals with that type of flows is called as meteorology. Okay, then we have oceanography. So anything involving fluid behaviors in ocean, that is called as oceanography. For example, you have the motion of submarines. So submarines are interacting with the ocean water. Okay, you have oil spillages in the ocean. Okay, you have sediments and debris flow in the ocean. Okay, so all these type of studies which are involving ocean and ocean ecosystem, these comes under the category of ocean. Similarly, there is one more branch which is called as hydrology. So what do you mean by hydrology? When we talk about water at surface of earth or below surface, for example, how the seepage of water is taking place into the ground, so that is coming below surface. So that particular branch of fluid mechanics is called as hydrology. Similarly, one important branch, even if you see in some of the institutes, there will be there is engineering also in its name, aerospace engineering. Okay, so the similar way, what we do in aerospace? So we typically consider the high-speed flying objects, aeroplanes, rockets, okay, space shuttles. So all these things are nothing but the high-speed flying objects. And when these high-speed flying objects interacts with the atmosphere, in the atmosphere we are having air as the main component, as the main gas, though it's a mixture of gas, but mostly it's having a homogeneous composition throughout. Okay, so when air is interacting with high speed objects, so typically when we study the external flow of high speed objects with the atmospheric air, then whatever the branch of fluid mechanics we are having, that we call as aerodynamics. Okay, so this is interaction of air with high speed objects. Particularly over here, I can refer the specific term atmospheric. Okay, so its interaction with aeroplanes, with rockets, with space shuttles, etc. So that comes because here important concepts will be coming. Formation of this lift, drag for controlling these objects, etc. Okay, so that comes under the categorization of aerodynamics. Apart from that, depending upon the specific application, there can be another name. For example, in present days, typically you might have observed during this COVID era, there was lots of interest on developing the biomedical equipment. Okay, particularly in our country. So if you see, initially there was need for ventilators, then there was need for oxygen. So initially people were trying to develop indigenous ventilators, then people were trying to develop indigenous oxygen concentrators. So everywhere what you are finding, then within the human body also, if say now people are trying to develop artificial hearts, okay, then for lungs already this ventilator is serving the purpose. So this type of equipment when we are considering which are involving the fluid mechanics, then typically we can call the name as biofluidics. Okay, so biofluidics is also one of the important applications. Then another important application which has grown typically in last few decades is that, and that is particularly involved with the development of this electronic industry. So if you see nowadays what is happening, all your mobile phone, laptops, their performance is increasing, okay, but their size is decreasing. And these are nothing but consisting of number of electronic, small electronic devices, and all these electronic devices generates heat. Okay. Typically from your earlier knowledge, if you see, whenever we are having the involvement of the heat, what we want? We want large area in order to dissipate that heat, because heat transfer in any mode, if you talk about either conduction, convection or radiation, is directly proportional to area. Fine. But here opposite is happening. So area is actually reducing because size is reducing. And if we are not able to remove the heat, you might have observed when your laptop is getting heated or when your mobile phone is getting warm, then actually it will not give its required or desired operations properly. Okay. And in some cases, even nowadays, the systems are provided with actually thermal cutoff also. So thermal cutoff happens and automatically the system gets shut down. Okay, this happens. So nowadays what we are trying to do, or what people are trying to do, is actually they are trying to fabricate very small channels through these, which will be passing through these electronic components, and the size of these channels can be of the order of say 5 micrometer or so. Okay, and they will be passing some high energy density carrying fluids or high conductivity fluids through these channels, so that these fluids can effectively extract the heat from these devices, so that these devices can be effectively cooled and these can work properly. Okay, so that is another say branch of fluid mechanics which is involving the fluids and is typically called as microfluids. Okay, so there can be different names depending upon the application area where the study of fluid is involved, but the main theme is nothing but fluid mechanics. So whatever the subject which we will be studying in this particular semester, this is actually the core subject of each of these application areas. So it means that if you want to develop the advanced knowledge in gas dynamics, advanced knowledge in say aerodynamics, or in biofluidics, microfluidics, for everything you first know the fundamental thing of fluid mechanics. If you are not knowing fluid mechanics, then you cannot effectively study all these other concepts. Okay, so you can see the importance and essence of the subject fluid mechanics, that is having even huge applications in the present day systems which we are developing. Now I will be going through the slides where I have first given some historical aspects, and after that I have actually given the application. So when you will be going through the application areas, you will be finding that how important is actually fluid dynamics. So typically you see the history of the fluid mechanics, which is nicely given in the form of a timeline over here, and the name of all the famous scientists which were involved in development of fluid dynamics theories. Okay, so in this, if you see, the very first name is Archimedes. Okay, so all of you know about the Archimedes principle. Okay, so Archimedes was the considered as the first one who has actually applied the fundamentals of fluid mechanics at that time to solve a problem. What was the problem? I am not remembering the name of the king, but in some king's crown they had to find the amount of gold. Okay, so at that time Archimedes had applied non-destructive method of buoyancy principle to find the amount of fluid in that graph. Okay. Then all these are very, very famous name. Then another important name over here is Daniel Bernoulli. So all of you know nowadays also study the Bernoulli's equation. So Daniel Bernoulli has written a text which was named Hydrodynamica, and Hydrodynamica is kind of considered as the first text of the fluid mechanics. So here in written form, some principles of fluid mechanics are actually available from the history. So these are available from Daniel Bernoulli. Okay, and you can see this Pascal, Newton. So Newton has given the Newton's law of motion, and their applicability to fluids is then done by Henry Navier. Then in Navier's equations are further simplified by Stokes. I am not finding the name here. So yeah, this is Stokes. So you can see Navier and Stokes are having some overlap of the time period. Okay. So whatever the work Navier has done, this was further continued by Stokes also. Okay. So that is why maybe at the moment you might be knowing the full details, but I am sure that all of you must have heard the name Navier-Stokes equations. Okay, at least name I think all of you must have heard. So Navier-Stokes equations, you can see the duration when these are actually developed. Okay, then one very, very important person over here in the study of fluid dynamics is actually Prandtl. So can you locate the name? Obviously Euler was also there, so Euler's equation of motion also you see. Okay, so Euler didn't consider the effect of viscosity. So Euler has given the equations only for ideal fluids which are having zero viscosity. Okay, then yeah, so Prandtl I am not able to locate. Maybe see Blasius, Poiseuille, Darcy. So all these things, whatever I am pointing out over here, you will be actually learning some of the concepts of fluid mechanics in this course by their name. So there is some flow which is called as Poiseuille flow. There is some flow which is called as Couette flow. So name of the Couette also you will be finding in this particular list. There is this important diagram which is called as Moody's diagram. Okay. There is one important equation which is called as Darcy's equation for estimation of pressure drop. Then there is, in the concepts of advanced fluid mechanics, we will try to see some of its concepts in this course as well, Blasius solution of boundary layer. Okay, so these are very, very important things. Then yes, you can see this important person, Ludwig Prandtl. So Prandtl has actually done very, very significant work in the development of the boundary layer theory. Okay, so boundary layer basically comes into picture when we study the flow of viscous fluids or interaction of viscous fluids with solids or other stationary fluid interfaces. Okay, so stationary or moving fluid interfaces. Okay, so Ludwig Prandtl's work was very, very important, and then after the Prandtl's work was carried by some of his students. So von Karman is one of the important student of Prandtl. So basically von Karman did his say research work with Prandtl. Okay, so he was student of Prandtl. So he has also then whatever the equations were developed by Prandtl, so he has given the approximate solution using the integral approach for these equations. Okay, so these are some of the important names. Now you can see one important thing on this history of the fluid mechanics is that this is the portion when the development of basic equations started. So this was the era, okay, when development of the basic equations started, and now this is the portion you can see somewhere close to say 1950 or 60 when development of advanced experimental and numerical methods started. Okay. So what was the earlier approach of solving fluid dynamics problem? So earlier approach was, we are having some set of equations, and these equations are nothing but partial differential equations. These partial differential equations we were trying to apply for very simplified geometrical configurations. For example, flow over a flat plate, flow over a cylinder, flow through a pipe. Very simplified configurations. So for this, analytical solution of partial differential equations were determined. Okay, but so this type of simple geometries does not come into application. In the application, we may have complex geometric structures. So for the finding complete analytical solution of all these partial differential equations for complex structure is actually not fully possible. So that is the reason people have started doing experiments, and along with the experiments, because experiments are not always easy, these are time consuming, and these are experiments involve huge amount of cost. Okay, so cost is also involved in doing the experiment. First you have to find the equipment, then you have to arrange it, there will be cost involved in purchasing the equipment, then there may be some consumables needed to perform the experiments, okay, which will be consumed in each experiment. For example, if you have to do the testing of engine, so what you have to do? You have to add lubricating oil, you have to add fuel, so that's a continuous cost. Whenever you want to do experiment, you have to spend for the fuel. Okay, so that is the reason that people try to find the alternate ways for solving the partial differential equations. Okay, and that is considered as the numerical methods. So advancements of numerical methods also started somewhere in 1970, and particularly its application for fluid dynamics started in somewhere in 1970. Okay, so if you see the study of computational fluid dynamics, so basically when we apply the numerical methods to fluid dynamics problems, then we refer the subject as computational fluid dynamics. Maybe some of you might be doing the computational fluid dynamics course as well. So there you will understand the essence of numerical methods in solving the fluid dynamics problems. Okay, so this is all about kind of brief summary about the historical developments in the subject of fluid dynamics. Okay, this is, you know, Reynolds, based on Reynolds number, we have one famous transition from laminar flow to turbulent flow. Okay, so Reynolds had developed one experimental facility at that time, and based on his experiment actually he has given the transition criteria that at what Reynolds number flow is changing from laminar to transition or transition to turbulent flow. Okay, so this is the photograph of original experimental setup of the Reynolds, and this photograph is taken in 1975 from University of Manchester, and this is the Leonard who is doing the experiment with this setup, who is standing in front of this experimental setup. So this photograph of the setup is from University of Manchester, which is taken somewhere in 1975. Okay, so you can see this is the original experiment which Reynolds has developed. So maybe after going through this course in the next semester or in the next year, you will be having one thermofluids lab 1, where you will be introduced to this type of setup in our lab here as well. Okay, now comes the applications of fluid dynamics. So you can see the very first application is nothing but our body itself. So in our body we have a heart which is continuously pumping the blood, and that blood is flowing through very small sized blood vessels, and you can imagine that the size and distribution of the blood vessels is so arranged that each blood vessel is getting the flow of the blood. Okay, then we have lungs over here. That is also involving the fluid, because these are nothing but helping us in breathing. Okay, then you can see this is a river. Okay, so in this river, lots of structures are there, lots of stones are there, rocks are there, and through these, this water is actually finding its path and then flowing. So what is the path of this fluid, why it is taking this path? So all these things actually we can answer with the help of principles of fluid mechanics. Then obviously birds you have seen flying, then how fish swims. So all these are nothing but the applications of the fluid mechanics in nature. Geographical flows. So geographical flows, I already told you that how the complete rain cycle is actually taking place. So this is nothing but a application of fluid dynamics at very large scale at atmospheric level. Okay. Engineering applications. Have you ever thought of why cars are of this shape and why buses and trucks are of flat head shape? Have you ever thought of why we are providing some sort of curvature to the car, but buses and trucks are coming with the flat head? Do you have any idea? Anyone is having any idea? Do you know about streamline objects? Why streamline objects are required for certain applications? To avoid air resistance, which is typically called as drag force. Okay, because more is the air resistance, more is the power you have to spend, more will be the requirement of the fuel. Your buses and trucks, these operates at lower speeds. At lower speeds, drag force is not that much high, because drag force is proportional to square of velocity, where your cars operates at very high speed. So the drag force generation in cars, etc., will be very high in comparison to buses and trucks, because they are operating at low speed. Okay, so that's why we need to prepare the shape of car something like this. So when we are preparing the shape of car something like this has not come someone's mind, okay, make this shape. You have to do a lot of trials. If this is the only shape, then why aeroplane is not of this shape? That is having some other shape. Okay. So depending upon the requirement, we have to do lot of experimentation, we have to do lot of analysis, we have to do numerical simulations in order to come to these conclusions. So this is nothing but, this is where we are finding the engineering applications of the subject fluid mechanics. So here you can see this is the model of a car, and over this car model some experiments are performed to determine the flow failure. And this is typical representation of a aeroplane at 3 different angles of attack. This is engine. So what happens? In this engine, a mixture of air and fuel is entering inside. So the fluid mechanics of this, like how it is mixing, what path it is taking, that is deciding the combustion characteristics within the engine. So if you are not having proper mixing of air and fuel, then what will happen? You will not get better combustion efficiency. Significant portion of the fluid of this fuel can come unburnt in the form of exhaust gases. Okay, so you see fluid mechanics is involved. And this is the impeller of a turbine. So over this impeller, you can see this different distribution of the pressure field over here. So this is particularly from, this photograph is particularly from a simulation work. Okay, numerical methods, using numerical methods is done. Then this is typically, you can see nothing but an electric artificial heart. So this is the artificial heart which is developed at Penn State University, and this particular photo is given in your book Senjal and Sembala because Professor Sembala, the second author of the book, is from Penn State University. Okay. Then when we do study the fluid mechanics problem, so as I told you, we can have three different approaches. One is theory, second approach is experiment, and third approach is simulation. So in theory, what we do? In theory, we try to find out the analytical method of governing equations. Sorry, analytical solution of governing equations, which are nothing but partial differential equations. In experiments, we will be employing some measurement equipment. So we will be taking measurements to determine the flow field. And in simulation, we will be using the numerical methods to solve governing equations. Okay. So analytical solution is mostly available for very simplified geometries. For complex geometries, it is very much challenging, and particularly with the advent of high-speed computers, people have majorly shifted towards the simulations work, because here numerical methods you can employ even for very complex problems where computers will be helping us in providing the solution. So that's why presently the major developments are taking place in the area of experiments and simulation. In order to give a comparison between the experiment and simulation, I have given you over here on the left side an experimental picture where a prototype of car is given, and over this you can see these laser rays are actually coming out. So this is nothing but laser setup of laser Doppler anemometry. So here they are employing these lasers and optical techniques to determine the flow field around this car. On the right hand side, this is a typical simulation setup where you can see this is the structure of a train. This is nothing but the structure of a train, and over the structure of the train they are trying to study the effect of crosswind. So from here crosswind is entering, then how this crosswind is actually splitting across the body of the train, that is something which is shown. Okay, is this point clear? So what we will do today, we will stop at this point, and then from the next lecture onwards we will try to study it in more details.